Some galaxies reveal their structure immediately. In visible light, their spiral arms, star clusters, and central bulges can be traced with relative clarity. Others present a different problem. Their central regions are physically sealed behind dust. In those systems, the nucleus, the compact inner zone where most of the energy is produced, is not merely faint, it is optically inaccessible. For decades, this has limited what astronomy could say about the chemistry of these environments because chemical identification depends on reading how matter interacts with light. This week's James Webb Space Telescope result belongs to that category of breakthroughs that are technical before they are dramatic. The headline is not a new image. It is a molecular inventory, extracted from a dust-buried galactic nucleus in a nearby ultra-luminous infrared galaxy. Ultra-luminous infrared galaxies are defined by the fact that they emit an exceptionally large fraction of their total energy in infrared light. The cause is straightforward. Dust grains absorb high-energy radiation and re-radiate it as heat, shifting the energy output into infrared wavelengths. The same process that makes these galaxies bright in infrared makes their central regions difficult to diagnose in visible light. Dust in astronomy is not smoke or soot in the everyday sense. It is a mixture of microscopic solid grains, often silicates, and carbon-rich material suspended in gas. These grains are highly effective at absorbing and scattering visible and ultraviolet radiation. Absorption transfers energy from incoming light into the grain, raising its temperature. The grain then emits thermal radiation, predominantly at longer wavelengths. In a dust-rich nucleus, that re-radiated infrared glow can dominate what is observable from outside the galaxy. This interaction between radiation and dust creates a paradox. The brightest power sources in the universe can be rendered invisible in visible light by the very material they heat. A nucleus can be producing extraordinary energy through intense star formation, through accretion onto a central black hole, or through a combination of both. Yet the central engine remains hidden in optical observations because dust converts direct light into diffuse infrared emission. Earlier observatories could measure how luminous the galaxy was in total infrared output, and they could infer that an energetic engine must be present. But inference is not the same as diagnosis. Without access to the chemical fingerprints of the buried gas, it has been difficult to test detailed models of what is happening inside. The new result matters because it moves beyond inference. It identifies a suite of carbon-bearing molecules inside an obscured nucleus where visible light provides almost no information. The key concept is spectroscopy. Spectroscopy is the measurement of light as a function of wavelength, separating a blended beam into its component colors, including colors outside the range of human vision. Molecules interact with light at specific wavelengths because their internal structures permit only certain energy transitions. In the infrared, those transitions often correspond to vibrations, bonds, stretching, bending, and twisting. Each molecule has a characteristic pattern, and that pattern can be detected when the molecule absorbs or emits infrared radiation. The reason infrared is decisive here is twofold. First, infrared light travels through dust more effectively than visible light. Dust opacity decreases at longer wavelengths, meaning infrared photons are less likely to be absorbed or scattered out of the line of sight. Second, many molecules have strong vibrational features in the mid-infrared. When infrared light from a hot background passes through cooler molecular gas, those molecules can remove narrow bands of wavelengths, leaving recognizable absorption features. Conversely, if molecular gas is warm enough and sufficiently excited, it can emit at its characteristic wavelengths, producing emission features. In both cases, the spectrum becomes a record of chemical composition. This week's Webb-based spectrum from a dust-buried nucleus contains evidence for small hydrocarbons. Hydrocarbons are molecules composed primarily of carbon and hydrogen. Their importance in astrochemistry is practical rather than philosophical. Carbon readily forms complex structures, including chains and rings, and hydrocarbon networks are common intermediate stages in broader chemical pathways that, under appropriate conditions, can lead to more elaborate organics. In the reported results, the identified species include ringed and chain-like molecules such as benzene, methane, acetylene, and longer carbon chain molecules. Evidence also points to a chemically reactive radical. A radical is a species with an unpaired electron, which makes it highly reactive and typically short-lived compared with stable molecules. The detection of a radical in an astrophysical environment is a sign that chemical reactions are actively occurring, because radicals tend to be rapidly consumed unless they are continually produced. The scientific tension lies in the environment. The nucleus of an ultra-luminous infrared galaxy is not chemically quiet. It is a region where gas densities can be high, where radiation fields can be intense, and where turbulence and shock waves may be common. If the nucleus is powered mainly by a starburst, meaning a concentrated burst of star formation, massive young stars produce strong ultraviolet radiation. Their stellar winds and eventual supernova explosions inject energy into the surrounding gas and dust. If the nucleus includes an actively accreting supermassive black hole, the central region can emit energetic radiation across the electromagnetic spectrum, and it can accelerate particles that further alter the chemistry of the surrounding medium. Both regimes are capable of destroying complex molecules. Ultraviolet photons can break chemical bonds. High temperatures can fragment molecules and reduce chemical complexity. Collisions in turbulent gas can disrupt delicate structures. A reasonable expectation would be that an environment so energetic would suppress the survival of small and medium-sized hydrocarbons. And yet the spectrum suggests that these molecules persist and may be abundant. The implication is not merely presence, it is balance. If the environment is destructive and the molecules are still detected strongly, then formation processes must be continually replenishing them. The system becomes a chemical steady state. Destruction occurs, but production keeps pace. That raises a mechanistic question. What processes can generate and maintain such a hydrocarbon-rich mixture inside a heavily obscured nucleus? There are several plausible drivers, and the observation provides constraints rather than final answers. One candidate involves dust grain processing. Carbon-rich dust grains and complex solid material can act as reservoirs of carbon. In harsh environments, energetic radiation or particle bombardment can erode grains, releasing smaller carbon-bearing fragments into the gas phase. Once in the gas phase, those fragments can participate in reaction networks that build up a family of hydrocarbons. Another candidate involves high-density chemistry. In dense gas, three-body interactions and rapid reaction sequences can proceed more efficiently, allowing certain molecules to form even under energetic conditions, as long as there are regions shielded from the most destructive radiation. A third candidate involves shock chemistry. Shock waves compress and heat gas locally. They can both destroy and create, breaking apart some structures while enabling reactions that would not occur at lower temperatures. A fourth candidate involves irradiation chemistry. Strong infrared and X-ray fields can drive ionization, producing charged species that react rapidly and can assemble new molecules through pathways unavailable in neutral gas. The responsible position is that the spectrum indicates chemical complexity in a setting where many models predicted it would be difficult to sustain. In the data favor active, ongoing chemistry, but the detailed balance between formation and destruction remains an area of research. This is where Webb's contribution is most concrete. It provides the measurement that forces models to become specific. The question is no longer whether complex hydrocarbons might exist in such nuclei. Evidence suggests they do. The question becomes which physical mechanisms, at what densities and temperatures, under what radiation fields, can reproduce the observed molecular pattern. The phrase, "building blocks of life," is often used in headlines because it is accessible. In a scientific sense, it needs careful framing. Hydrocarbons such as methane, acetylene, and benzene are not biological molecules. Their presence does not indicate life. What they indicate is that carbon chemistry is active in a range of environments across the universe, including environments previously inaccessible to detailed chemical analysis. In astrobiology, the study of the origins and distribution of life and its precursors, such results matter because they establish that prebiotic chemistry, meaning chemistry capable of producing molecules that can later participate in biological pathways, is not confined to gentle settings like cold molecular clouds or planet-forming disks. It can also occur in heavily obscured, high-energy galactic nuclei, although the relevance of those environments to life depends on whether the molecules can survive transport and whether they can contribute to chemical evolution in more hospitable regions. The broader consequence is methodological. By demonstrating that mid-infrared spectroscopy can recover molecular information from a dust-buried nucleus, Webb extends astrochemistry beyond the Milky Way into extreme extragalactic environments. That capability changes the research landscape. It allows comparisons across different types of infrared galaxies, across different energy sources, and across different dust geometries. It also opens the possibility of tracking how organic chemistry evolves with cosmic time by studying more distant systems where the same physical processes were common during earlier epochs of galaxy evolution. To understand why the conclusion is credible and why the chemical identifications are not merely interpretive, the next step is to examine how Webb reads chemistry through dust. That means following the measurement process itself, how infrared spectroscopy isolates molecular fingerprints, how features are separated from dust absorption bands, and how scientists test alternative explanations before assigning a molecule to a specific feature in the spectrum. The mechanisms of detection are essential because in an obscured nucleus, the spectrum is not simply a chemical list. It is a layered record of light passing through complex material, and it must be analyzed with discipline before it can be trusted. The credibility of a molecular claim in astronomy is never secured by a single impressive plot. It is secured by method, by whether the measurement isolates a signal that has a known physical origin, and by whether alternative explanations have been systematically reduced in a dust-buried galactic nucleus. This requirement becomes stricter because the spectrum is not a clean view of one layer of gas. It is a composite of thermal emission from dust, absorption by dust, emission and absorption by molecules, and the geometry of the region itself. The James Webb Space Telescope makes this kind of work possible because it is designed to measure infrared light with exceptional sensitivity and stability, and because its instruments can record spectra at wavelengths where two crucial things are true at the same time. Dust becomes more transparent than it is in visible light, and molecular vibrational fingerprints become strong. The observation does not remove dust from the system. It exploits the fact that dust, while obscuring at short wavelengths, is also a bright infrared background, and that background becomes the illumination source against which molecules can be detected. To see why, imagine the nucleus as layered material wrapped around a furnace. The furnace is the power source, a compact region where energy is produced by intense star formation, by matter falling into a central black hole, or by both. Around it is a dense medium of gas and dust. The dust grains absorb energetic radiation and heat up. As they heat, they emit a smooth continuum of infrared light, meaning a broad, relatively featureless glow spread across many wavelengths. That continuum is not noise, it is the backlight. If cooler gas lies between the hot dust and the telescope, the molecules in that gas can selectively absorb certain wavelengths from the continuum. The result is a spectrum that looks like a smooth curve with carefully placed notches. Those notches are not random. Their positions in wavelength space correspond to the internal vibrational modes of specific molecules. This is where the word spectroscopy earns its weight. Spectroscopy is not just the act of dispersing light. It is the practice of linking measured features to physical transitions in matter. In the mid-infrared, molecules primarily announce themselves through vibrations. A molecule's atoms are not fixed in place, they oscillate. Chemical bonds act like springs. Atoms stretch away from each other, bend toward each other, twist around bonds. Each distinct mode has a characteristic energy, and therefore a characteristic wavelength of infrared light that can be absorbed or emitted. And if you know the molecule and you know the physics of its bonds, you can predict where those features should occur. If you measure a set of features at those wavelengths, and they share the expected relative shapes, you can make a controlled identification. The identification is strengthened when multiple features from the same molecule appear together. A single dip could be coincidental or caused by something else. A consistent pattern across the spectrum is harder to imitate. This is why, in careful work, the analysis rarely rests on one feature alone. Researchers look for families of features that fit one molecule's expected signature and do not conflict with the signatures of other plausible contributors. They also test whether dust absorption bands could mimic the same pattern. Dust grains, especially when coated with ices or containing certain lattice structures, can produce broad absorption features. Those dust features tend to be wide and smooth compared with many molecular lines, but in a complex spectrum, there can be overlap. Distinguishing them requires both spectral resolution, meaning the ability to separate closely spaced wavelengths, and a model of the dust continuum, meaning an estimate of what the spectrum would look like if only dust were present. The mid-infrared is particularly suitable for hydrocarbons because many carbon-hydrogen bonds have strong vibrational modes in this range. A carbon-hydrogen bond can stretch, and that stretching absorbs or emits at characteristic wavelengths. Carbon-carbon bonds can also vibrate. Ring structures like benzene have collective modes where the ring breathes, bending and stretching in coordinated patterns that produce distinctive features. Smaller molecules like methane have their own vibrational modes, often in clusters, that can be identified if the spectrum is sensitive and the background is bright enough. Longer carbon chain molecules have modes that can overlap, but they can still contribute recognizable patterns when present in significant amounts. In the context of a dust-buried nucleus, it matters that these molecules are being detected against the thermal continuum of hot dust. The dust continuum supplies the photons. The molecules impose structure. The measurement is a contrast problem. The telescope must measure a smooth background precisely enough that it can detect the relatively subtle deviations created by molecular absorption and emission. This is where instrument stability becomes as important as raw sensitivity. Small calibration errors can masquerade as features or erase them. Webb's design, including its location far from Earth's heat and its cold operating environment, reduces instrumental noise and makes stable infrared spectroscopy feasible in a way that previous missions could only approach for certain targets. However, even with a stable instrument, the interpretation remains dependent on geometry. A spectrum is not a photograph. It is the integrated light from whatever lies within the observing aperture, combined along the line of sight. In a buried nucleus, there can be multiple components: extremely hot dust, close to the power source; cooler dust farther out; dense gas clumps; diffuse gas; and perhaps outflowing material. Some of those components might produce emission features, while others produce absorption. If a warm molecular layer sits on top of a hotter dust background, it can create absorption. If the molecular layer is itself heated and not strongly backlit, it can produce emission. If there are both, the spectrum can show a mixture. The same molecule can even appear in absorption at one wavelength and in emission at another, depending on the local temperature distribution and optical depth, a term that describes how opaque a medium is to a given wavelength of light. Optical depth matters because it determines whether the light you see is coming from deep layers or only from the surface. In a highly opaque region, you may only see the outermost layer at a given wavelength. In a less opaque region, you see deeper. In an obscured nucleus, the optical depth can vary strongly with wavelength. Shorter wavelengths may be blocked almost completely. Longer wavelengths may pass through more easily. This wavelength-dependent transparency means that different parts of the spectrum can probe different depths. That complicates interpretation, but it also provides leverage. By analyzing how features change across wavelengths, researchers can infer whether molecules reside in surface layers, deeper shielded zones, or in regions where dust and gas are intermixed. To build confidence, researchers typically follow a sequence of checks. They begin by fitting the dust continuum, because without a baseline, there is no way to define the depth of absorption features. Continuum fitting is not arbitrary curve drawing. It is guided by physical models of dust emission, including dust temperature distributions and emissivity, which describes how efficiently dust emits at different wavelengths. Once a plausible continuum is established, features are measured relative to it. Researchers then compare those features to laboratory and theoretical spectral libraries. These libraries contain the known infrared absorption and emission characteristics of molecules measured under controlled conditions or computed from molecular physics. When a match appears, the researchers test whether other molecules could explain the same features, especially in crowded spectral regions. The analysis becomes a process of elimination as much as recognition. In this week's case, the identified hydrocarbons include both simple molecules and more structurally specific ones. Structural specificity matters because certain molecules have signatures that are harder to confuse. A ringed molecule like benzene has vibrational modes that reflect the symmetry and bond structure of the ring. While no identification is beyond question, ring signatures are typically more distinctive than those of very simple fragments which can overlap with many other species. The presence of methane and acetylene, if confirmed through multiple features, indicates that the chemical network includes both saturated molecules, meaning molecules with the maximum number of hydrogen atoms attached to carbon, and unsaturated molecules, meaning molecules with multiple bonds that make them chemically more reactive. The coexistence of both suggests a dynamic environment where hydrogenation and dehydrogenation processes occur. Hydrogenation is the addition of hydrogen atoms to a molecule, often occurring on the surfaces of dust grains or through reactions in the gas. Dehydrogenation is the removal of hydrogen, which can occur under energetic irradiation or high temperatures. When both types of molecules appear, it implies that neither process is dominating absolutely. Instead, the system is maintaining a mixture through ongoing reactions. The detection of a radical strengthens that impression. A radical's defining feature, the unpaired electron, makes it eager to react, often within short timescales, if it encounters compatible partners. In dense gas, radicals can be quickly consumed. In strong radiation fields, radicals can also be generated continuously as photons break bonds in larger molecules. Therefore, a radical signature, and especially if it appears alongside a suite of stable hydrocarbons, points to a chemical ecosystem driven by energy input. Energy breaks bonds and produces reactive fragments. Reactions rebuild stable molecules. The cycle repeats. This is a plausible equilibrium in an environment dominated by intense radiation and high densities, precisely the conditions expected near the hidden engines of ultra-luminous infrared galaxies. Another layer of inference comes from relative strengths. Spectroscopy does not usually deliver a simple count of molecules. It delivers features whose depths or heights are linked to column density, meaning the number of molecules integrated along the line of sight. Translating feature strength into column density requires assumptions about temperature because molecular populations across vibrational states depend on temperature. It also requires assumptions about how uniformly the molecules cover the background source. If the molecular gas covers only part of the dust continuum, absorption features may appear weaker even if the local abundance is high. This effect is called covering fraction. Therefore, when researchers report abundance estimates, they usually describe them as model-dependent. The evidence can be strong that a molecule is present. The exact quantity often has a range. It is also essential to distinguish between the presence of hydrocarbons and the claim that they are precursors to life. In a documentary context, the careful framing is that hydrocarbons are part of a broader carbon chemistry that, in some environments, can lead toward amino acids, nucleobases, and other biologically relevant compounds. But that pathway is neither inevitable nor universal. The nucleus of an ultra-luminous infrared galaxy is likely too energetic and too dynamic to host stable, long-lived prebiotic evolution in the way a calm planetary environment might. The significance is different. It shows that carbon chemistry can assemble complex structures under conditions that include strong radiation and high dust densities, and it suggests that galaxies may produce and redistribute organic material that later becomes incorporated into more benign environments. The redistribution point is not an embellishment. Galaxies are not closed containers. Gas and dust flow. Starbursts and accreting black holes can drive outflows, pushing material from the nucleus into the wider galaxy, or even beyond it. If hydrocarbons and related organics are present in the nucleus, some fraction of that material may be transported outward, mixed into colder regions where it can survive longer and participate in different chemical networks. Whether this happens efficiently and whether the molecules survive the journey are open questions that depend on the physical conditions of the outflow, the radiation field, and the density of the gas. But Webb's ability to identify molecules in the nucleus creates the possibility of testing these ideas by comparing nuclear chemistry to chemistry observed in outflowing gas or in the surrounding interstellar medium. This is the deeper methodological shift. Previously, astrochemistry could make its strongest claims in nearby, relatively calm environments: dense clouds, star-forming regions, planetary disks. Extragalactic astrochemistry existed, but it was limited in molecular specificity, especially for heavily obscured targets. With Webb's mid-infrared spectra, the field can now ask whether the chemical signatures of obscured nuclei resemble those of certain Milky Way environments, or whether they represent a distinct regime with its own dominant pathways. It can also examine how chemistry changes when the central energy source changes. If one galaxy's nucleus is dominated by a starburst, its radiation field may be strong in ultraviolet, but distributed across many massive stars. If another nucleus is dominated by a feeding black hole, the radiation may extend to X-rays with different spatial structure. Those differences should alter ionization rates and reaction pathways, and therefore molecular inventories. Mass spectroscopy can become a diagnostic of the hidden engine itself, but the method only works if the community trusts that the features are real and the identifications are disciplined. That is why the next layer of analysis must address the environment directly. It is not enough to say the molecules exist. It is necessary to explain how they could exist there. A credible explanation must track cause and effect across physical processes, how dust grains, radiation, shocks, and high-density gas together create a chemical network that can both break and rebuild hydrocarbons. That is where the scientific tension sharpens, because the same processes that can produce these molecules can also destroy them, and the observed spectrum suggests the balance has tipped toward persistence. The next section follows that balance into the nucleus itself. It moves from measurement to mechanism, asking what conditions would continually regenerate hydrocarbons, what the detected mix implies about temperature and irradiation, and why certain molecules, particularly ring structures and reactive radicals, constrain the possible chemical pathways. The observational claim opens the door. The physical explanation determines whether the door leads to understanding or merely to a longer list of mysteries. A molecular spectrum is not a catalog floating in isolation. It is a constraint on a physical environment. When a buried galactic nucleus shows hydrocarbons that include both small, stable molecules and reactive fragments, the observation immediately becomes a test of competing mechanisms. Something must be creating these molecules under conditions that also threaten to erase them. The nucleus, not by definition, is energetic. Yet the chemistry indicates persistence, and persistence implies replenishment. Start with the basic ingredients. Carbon and hydrogen are abundant. They arrive in the nucleus through the ordinary cycling of galactic matter. Gas flows inward under gravity. Dust grains, assembled over long time scales in stellar winds and supernova remnants, ride along with that gas. The question is not whether carbon is present. The question is what form the carbon takes and how energy reshapes it. In a heavily obscured nucleus, much of the carbon is likely locked into solid grains and larger carbonaceous structures, rather than entirely in simple gas phase molecules. That matters because solids are not inert. Under intense radiation and particle bombardment, solid carbon-rich material can be processed, eroded, and restructured. The nucleus can operate as a refinery, continually converting solid carbon reservoirs into smaller fragments that enter the gas phase, where they participate in a network of reactions. This processing is one of the most plausible routes to explaining why small hydrocarbons appear where they seem least likely to survive. In calmer regions of interstellar space, dust grains can be thought of as passive surfaces on which atoms and molecules stick, meet, and react. In an energetic nucleus, grains become reactive participants. Energetic photons, especially ultraviolet and X-ray photons, can knock electrons free, ionizing atoms and molecules and altering how reactions proceed. Energetic particles, including protons and heavier ions, accelerated by shocks or by the environment around an actively accreting black hole, can collide with grains and sputter material from their surfaces, meaning they physically eject atoms and small clusters into the gas. High temperatures can also cause volatile material, including small organics and ices, to evaporate from grains. Each process transfers carbon from solids into gas in forms that can be rebuilt into molecules like methane, acetylene, and benzene. The presence of both saturated and unsaturated hydrocarbons is an important clue. Saturated molecules, such as methane, hold as many hydrogen atoms as their carbon skeleton allows. Unsaturated molecules, such as acetylene, have multiple bonds that make them more chemically active. A mix of both suggests that the chemistry is being driven in multiple directions at once. Hydrogenation, the addition of hydrogen atoms, can occur efficiently on dust grain surfaces where hydrogen atoms are mobile and can attach to carbon-containing fragments. Dehydrogenation, the removal of hydrogen, can occur under energetic radiation that strips hydrogen atoms away or breaks carbon-hydrogen bonds. If a nucleus shows evidence for both kinds of molecules, then neither hydrogenation nor dehydrogenation is dominating completely across the entire region. Instead, the nucleus likely contains multiple zones, some where shielding and dense gas favor hydrogen-rich chemistry, and others where irradiation and heat favor hydrogen-poor fragments. In astrochemistry, shielding is not an abstract idea. It is a measurable physical effect. Dust and gas can block the most destructive photons, especially ultraviolet, and reduce the photodissociation rate, the rate at which molecules are broken apart by light. In a nucleus packed with dust, it is reasonable to expect small pockets or layers where molecules can survive longer because the radiation field is attenuated. However, the same dust that shields also heats and emits infrared light. The spectrum indicates that the environment is both luminous and obscured, which implies strong gradients. A hot inner zone may be too harsh for many molecules, but slightly farther out there may be dense, warm regions that are shielded enough for hydrocarbons to exist while still being exposed to energy that drives chemical reactions. This is where the idea of a chemical steady state becomes more than a metaphor. Imagine a region where the formation rate of a hydrocarbon equals its destruction rate. The molecule does not have to be long-lived in an absolute sense. It only has to be continuously produced. This is especially relevant for radicals. A radical, by having an unpaired electron, tends to react quickly. If radicals are detected, the simplest explanation is not that they are stable, but that they are being generated. Generation can occur when energetic photons or particles break larger molecules into fragments. It can also occur in high-temperature reactions that produce radicals as intermediates. In either case, radicals are a signature of a chemical engine running in real time. Consider benzene, the simplest aromatic ring. Aromatic means that the molecule contains a ring of carbon atoms with a particular electron structure that stabilizes the ring. Benzene is chemically significant because ring formation is not trivial. A ring is a closed structure. It is not a straight chain that can simply be extended. In many environments, forming a ring requires either a sequence of reactions that gradually bends a chain and closes it, or the assembly of smaller pieces under conditions where the ring becomes a stable endpoint. Detecting benzene suggests that the nucleus does not only fragment carbon, it also assembles it into structured forms. How might benzene form in such a setting? Several pathways are plausible, and the evidence can help discriminate, although it may not uniquely identify one route. One class of pathways involves ion-molecule chemistry. Ion-molecule reactions occur when a charged species reacts with a neutral molecule. These reactions can be fast, especially at the temperatures and densities expected in active nuclei. Ionization can be driven by energetic photons or by cosmic rays, meaning high-energy particles that permeate interstellar space and can be enhanced in starburst regions. When ionization rates are high, carbon can be driven into reactive ionic forms that build up larger hydrocarbons through successive additions of small molecules, such as acetylene, followed by rearrangements that close into rings. Another class involves neutral-neutral reactions at elevated temperatures. In very warm gas, certain neutral reactions that are slow in cold clouds can proceed rapidly enough to contribute. A third class involves grain surface chemistry, where carbon fragments stick to dust grains, react, and then are released back into the gas phase through heating or energetic processing. Each pathway has a different implication for the physical conditions. Ion-molecule pathways imply high ionization and a substantial supply of small building units. Neutral-neutral pathways imply higher temperatures in at least parts of the gas. Grain surface pathways imply that dust is not merely present, but actively cycling material between solid and gas. A buried nucleus likely includes elements of all three. The spectrum, by showing a suite of molecules rather than a single species, provides a way to narrow the balance. If acetylene is prominent, it can serve as a feedstock for larger carbon structures. If methane is prominent, it indicates regions where hydrogenation is effective. If longer carbon chains appear, it suggests that growth processes are proceeding beyond the smallest molecules. If a radical is present, it suggests active fragmentation and irradiation chemistry. The most demanding part of the explanation is the survival problem. Even if formation pathways exist, the nucleus is still an environment where destruction is expected. How do these molecules avoid being erased immediately? The simplest answer is spatial separation in a complex medium. The energy source, whether a starburst or an accreting black hole, is compact. The densest dust and gas are not uniform shells. They are clumpy and filamentary. Radiation may carve channels through lower density regions while leaving dense clumps shielded. In those shielded clumps, molecules can survive longer. Meanwhile, the overall infrared glow is dominated by dust, so the spectrum can integrate signals from both exposed and protected regions. This means the molecules detected do not need to fill the entire nucleus. They need to occupy enough of the line of sight and cover enough of the infrared background to leave measurable features. This clumpiness also connects to why these galaxies are so infrared bright. Ultra-luminous infrared galaxies often arise from interactions or mergers which funnel gas into the central regions. High gas densities can trigger intense star formation. High densities also increase the probability of shielding because more material lies between the energy source and a given region of gas. The same inflow that powers the luminosity can create pockets where chemistry can proceed under partial protection. In such pockets, the chemical network can be surprisingly productive because high density increases reaction rates. When densities rise, molecules collide more often. That alone does not guarantee complexity, but it allows certain reaction pathways to compete successfully against destruction, especially if the destruction is dominated by photons that are attenuated in dense regions. There is another mechanism that can tip the balance: rapid cycling between phases. In an active nucleus, dust grains can be heated and cooled repeatedly as they move through different zones. Gas can be compressed by shocks and then expand. Molecules can form on grains, be released into the gas when grains warm, and then be processed by radiation into different forms, some of which return to grains. The chemistry becomes less like a quiet equilibrium and more like a circuit. Energy is injected, material is transformed, and the products are not static. This perspective helps make sense of why both stable molecules and reactive fragments might be present at the same time. Shocks deserve special attention because they are both destructive and creative. A shock wave is a compressive disturbance that travels through gas, abruptly raising temperature and density. Shocks can be generated by supernova explosions, by powerful stellar winds, by jets and outflows from a central black hole, or by collisions between gas streams in a turbulent nucleus. In a shock, molecules can be broken by collisions, but shocks can also liberate material from grains, injecting fresh carbon-bearing fragments into the gas. Immediately after the shock passes, the gas cools. In the cooling post-shock region, reactions can proceed rapidly, sometimes producing molecules in quantities that would not arise in steady conditions. If a nucleus is threaded by repeated shocks, it can maintain a constant supply of chemically reactive material. Radiation-driven chemistry adds another layer. Energetic photons can create ions and radicals. In environments dominated by X-rays, ionization can penetrate deeper into dense gas than ultraviolet photons can, because X-rays have higher energies and can travel farther before being absorbed. This can create extended zones where ionization remains significant even when the region is dusty and dense. Ionization is chemically consequential because it opens reaction pathways that are otherwise blocked. Charged species attract neutrals, and the resulting reactions can proceed without the large activation barriers that limit neutral reactions at lower temperatures. When ionization is sustained, chemical networks can assemble hydrocarbons efficiently, even in hostile environments, as long as some shielding prevents complete photodissociation. The spectrum's implication of abundant hydrocarbons therefore points toward a combined picture: dense, dusty gas providing shielding and high collision rates, strong radiation and shocks, providing continuous fragmentation and ionization. Dust grains serving as both shield and reservoir, and dynamic flows, cycling material through different physical regimes. The environment is not chemically sterile, it is chemically forced. This is the place where responsible uncertainty must be explicit. The evidence supports the presence of specific molecules and suggests active chemistry, but translating that into a single dominant mechanism requires additional observations. The relative contribution of starburst activity versus black hole accretion matters because the shape and penetration of the radiation field differs. The distribution of gas density matters because shielding and reaction rates depend on it. The role of shocks depends on the dynamical history of the nucleus. Models indicate that different combinations of these factors can produce overlapping molecular signatures, and distinguishing between them will require comparing multiple galaxies and examining how molecular features correlate with other indicators of the nuclear power source. But even without a single mechanism identified, the implication is already strong. Chemical complexity can be maintained in an obscured nucleus through continual replenishment. That moves the discussion beyond the superficial question of whether a molecule can survive there. The more accurate question is whether the physical environment can sustain a chemical production line. This week's observation suggests that, in at least one such nucleus, it can. The remaining question is what this means outside the nucleus. If the chemistry is being driven and replenished under extreme conditions, does it remain trapped there as a local curiosity, or does it become part of the galaxy's wider material cycle? The answer depends on transport, on whether outflows, winds, and turbulent mixing can carry carbon-bearing molecules or their precursors out of the hidden core into regions where they can persist longer and influence later stages of chemical evolution. That is the next logical step, because the significance of molecular production is not only the fact of production, but the fate of the products. The next section follows that fate. It examines how material moves out of dust-buried nuclei, how molecules might be destroyed or preserved during transport, and what it would mean, scientifically and cautiously, to connect a molecular inventory in a hidden galactic core to the broader question of how the universe distributes the raw ingredients of complex chemistry. Material does not remain confined to a galactic nucleus. The same processes that make an ultra-luminous infrared galaxy bright also tend to make it restless. When large amounts of gas are funneled into the center, pressure builds. Radiation heats dust, dust heats gas. Young massive stars and supernova explosions inject momentum. And if a central black hole is actively accreting, it can add an additional source of mechanical power through winds and, in some systems, collimated jets. The result is movement. Gas flows inward to feed the engine, but gas can also be driven outward, carrying dust and molecules with it. The chemical inventory detected by the James Webb Space Telescope therefore leads to a decisive question. Is the obscured nucleus merely a chemically active chamber, or is it a producer whose output can influence the galaxy beyond the central region? And this is not a philosophical framing, it is a physical problem. If hydrocarbons are formed or replenished in the nucleus, their significance depends on transport and survival. A molecule formed in dense, shielded gas may be exposed to harsher conditions as it moves outward. If it is destroyed quickly, the chemical richness remains local. If it survives or is transformed into other compounds that are more resilient, the nucleus becomes a contributor to the galaxy's wider carbon chemistry. Outflows provide the most direct transport route. An outflow is a large-scale movement of gas away from the nucleus, often measured through broad spectral lines, blue-shifted absorption features, or spatially extended emission that indicates motion along the line of sight. Outflows can be driven by different engines. In starburst-dominated nuclei, collective stellar winds and repeated supernova explosions can create a hot, overpressurized medium that vents along the paths of least resistance, producing a galactic wind. In nuclei influenced by accretion onto a supermassive black hole, winds can be launched from the accretion disk, and in some cases, jets can accelerate and heat surrounding material. Observations across many galaxies indicate that both star formation and black hole activity can drive outflows. The dominant driver varies by system. In the context of this week's Webb result, the precise driver matters because it influences the outflow's temperature, ionization state, and speed, all of which affect molecular survival. Survival is not an all-or-nothing condition. Molecules can be destroyed by ultraviolet radiation, by energetic particle collisions, and by high-temperature reactions, but outflows are not homogeneous. They can contain dense clumps embedded within more diffuse hot gas. Dense clumps can provide shielding, reducing the exposure of interior molecules to destructive radiation. They can also cool more effectively. Cooling matters because many molecules are stable only below certain temperatures. If outflowing gas remains too hot for too long, molecules will fragment. If pockets cool and remain dense, molecules can persist. This clumpy, multi-phase structure is not speculative decoration. It is often required by observations of outflows that show molecular material moving at high speeds. In several well-studied galaxies, molecular gas has been observed in outflows, indicating that at least some molecules can be transported from central regions into the wider galaxy. Whether the specific hydrocarbons identified in the obscured nucleus are among the transported species is uncertain. Small hydrocarbons can be both fragile and reformable, meaning they may be destroyed in one zone but reformed in another, especially if carbon-bearing fragments and hydrogen remain abundant. Therefore, the more precise scientific question becomes, does the nuclear chemistry seed an outward-moving medium with carbon-rich fragments that enable hydrocarbon chemistry farther out, even if the molecules themselves do not survive intact? To answer this in a disciplined way, the chemical inventory must be understood as both product and diagnostic. The presence of ring structures and longer carbon chains suggests that carbon is not only being broken down, it is also being assembled into stable frameworks. Aromatic rings, in particular, can be relatively resilient because their electron structure stabilizes the molecule against certain forms of disruption. That does not make them indestructible, but it changes the expected balance. If aromatic compounds are present in significant quantities in the nucleus, they may represent a durable fraction of the carbon chemistry that has a better chance of surviving transport than more reactive species. Even if benzene itself does not survive, the processes that form it may also produce larger aromatic structures, some of which can be more robust. The mid-infrared spectral region is known to include signatures from a broader class of aromatic-like materials, and while careful analysis distinguishes specific molecules from broader features, the general point remains: ring chemistry is a sign of carbon organizing into frameworks that can persist under more conditions than fragile radicals can. Radicals, by contrast, speak to immediacy. If radicals are detected in the buried nucleus, they likely reflect ongoing irradiation and fragmentation. In an outflow, radicals may be produced in the interfaces where fast winds collide with denser clouds, generating shocks that break bonds and produce reactive fragments. Those fragments can then recombine into stable molecules as the gas cools. In this way, the nuclear environment and the outflow environment could share a common mechanism: continuous cycling between destruction and formation. The nucleus would not simply export finished molecules, it would export a physical regime, a set of conditions and materials that keeps carbon chemistry active as gas moves outward. This leads directly into the building blocks language and its limits. In scientific terms, the molecules detected represent a subset of carbon chemistry that is relevant to prebiotic pathways, but relevance does not imply destiny. Life, as far as current evidence indicates, requires sustained chemical complexity in stable environments, with long-term energy gradients and mechanisms for concentration and selection. A dust-buried galactic nucleus is not that environment. It is too energetic, too dynamic, and too far from the controlled conditions that appear necessary for prebiotic evolution to progress toward biology. What the nucleus may contribute is not a cradle of life, but a distribution network for carbon complexity. If complex organics can be produced and exported into colder regions where they can persist, they may become incorporated into molecular clouds, into star-forming regions, and eventually into planet-forming material. In that sense, the nucleus could contribute indirectly to the chemical richness from which habitable systems draw. The logic here depends on timescales. A galaxy evolves over hundreds of millions to billions of years. Starbursts can last tens of millions of years. Outflows can persist across comparable timescales. If a nucleus repeatedly produces carbon-rich material and outflows repeatedly distribute it, then the integrated effect over cosmic time can be substantial, even if any single molecule's lifetime is short. The contribution is statistical and cumulative. Individual hydrocarbons may be transient, but the chemical reservoir of carbon-bearing material they represent can be persistent through continual replenishment. The James Webb Space Telescope now makes it possible to test this with observations rather than speculation, because it can measure chemistry in both obscured cores and, potentially, in the surrounding regions where material is transported. The key is comparative spectroscopy. If the nucleus shows strong signatures of specific hydrocarbons and aromatic ring chemistry, and if outflow regions or circumnuclear zones show related signatures, then a link becomes plausible. If the surrounding regions show different chemical inventories, then the nucleus may be chemically distinct, and its products may be rapidly transformed or destroyed. Both outcomes are informative because they constrain the transport and processing pathways. There is another, broader implication that does not require outflows to carry intact molecules: the role of obscured nuclei as chemical laboratories for extreme conditions. Much of astrochemistry has been built on observations of relatively cold and relatively nearby environments. These environments are chemically rich, but they represent one regime. A dust-buried nucleus represents another regime, one characterized by high densities, strong radiation fields, intense infrared backgrounds, and complex geometry. By demonstrating that specific hydrocarbons can be detected in this regime, the Webb result extends the domain of chemical measurement and forces chemical theory to operate under a wider range of physical conditions. In practical terms, then this changes how astronomers interpret infrared bright galaxies across the universe. Ultra-luminous infrared galaxies are not rare in the distant universe. They were more common during earlier epochs when galaxy interactions and intense star formation were more frequent. If obscured nuclei routinely host active hydrocarbon chemistry, then the integrated production of carbon-bearing molecules across cosmic history could be larger than previously estimated. This does not mean that early galaxies were filled with life-related molecules in any direct sense. It means that carbon complexity may be a persistent companion to energetic galaxy evolution. At this point, responsible uncertainty is not optional. The current result is strong evidence for a specific molecular set in a specific nucleus, but generalizing requires a sample. Different nuclei have different balances of starburst and black hole power, different dust geometries, and different histories of gas inflow. Chemical inventories may vary accordingly. In addition, spectral interpretation can be sensitive to temperature distributions and to the covering fraction of molecular gas. A molecule can appear prominent if it sits in the right geometry relative to the infrared background. Therefore, the next phase of research must include repeated observations across multiple systems, analyzed with consistent methods to distinguish genuine chemical diversity from observational selection effects. Even the phrase "dust blocked" must be handled carefully. Dust blocks visible light efficiently, but it does not block all information. Dust also emits, and in emitting it creates a bright continuum that can be used as a backlight for absorption spectroscopy. The nucleus is not invisible. It is translated into infrared. Webb's contribution is to exploit that translation at the wavelengths where molecules are legible. This reframing matters because it suggests that hidden regions across astronomy may not be beyond reach. They may require the right wavelength, the right sensitivity, and the right analytical discipline. The discipline is as important as the instrument. A chemically rich spectrum is tempting to overinterpret. The most responsible outcome of this week's result is not to inflate the claim into a declaration about life. It is to recognize what the data truly accomplish. They demonstrate that complex hydrocarbon chemistry can exist and likely be maintained in an obscured nucleus with extreme energy input. They provide a measured molecular pattern that models must reproduce. They suggest that dust, rather than being a barrier to chemical understanding, can become the enabling medium through which chemistry is read. The controlled tension in this result is therefore not narrative. It is methodological. The universe has placed an active chemical environment behind a thick screen of dust. For decades, astronomers could measure the glow, but not the composition. Now the chemical composition is emerging, not as a vague hint, but as identifiable species with specific vibrational fingerprints. That shifts the scientific conversation from what might be inside to what conditions must exist for this chemistry to persist, and how common are these conditions? The next questions are already implied by the spectrum. If benzene and related hydrocarbons appear in one obscured nucleus, do they appear in many? Does the presence of these molecules correlate with indicators of star formation or with indicators of black hole accretion? Do different dust temperatures and optical depths produce systematically different chemical inventories? Can Webb detect similar chemistry in more distant galaxies, pushing this kind of analysis deeper into cosmic time? And perhaps most consequentially, for understanding galaxy evolution, do these chemical signatures change As a merger progresses and the nucleus becomes more compact and more obscured, and then later clears as outflows and feedback disperse the dust. These questions lead to a new kind of mapping, not a map of where stars are, but a map of where chemical regimes exist in the most obscured, energetic regions of galaxies. If Webb can build such a map across a representative sample, it will not only expand astrochemistry, it will provide a new diagnostic of how galaxies convert gas into stars, how black holes influence their environments, and how matter cycles from dense, hidden cores into the broader interstellar medium. What began as a list of molecules therefore ends as a constraint on the life cycle of galaxies. The detection of hydrocarbons in a dust-buried nucleus is evidence that carbon chemistry is not a fragile side effect confined to quiet regions. It can be an active component of the most intense phases of galactic evolution. The immediate work ahead is to confirm, compare, and model. The larger consequence is that the chemical universe is proving to be accessible in places where, until now, it was effectively sealed.